So in this problem we have a mass that's 20 meters high, goes down a ramp, and during this whole time period we'll call this A, this region A, alright? It has a coefficient of kinetic friction of 0. And during region B, it has a kinetic friction of 0.5 or a half. Okay, so our first task is to determine the speed when the block is at this point, right before it goes into region B. So the first thing we notice is that since there is no kinetic friction, all of the energy from this point, which is all potential energy, there is no kinetic energy at this point, meaning there is no velocity at this point. Okay? So all of the potential energy got converted to kinetic energy. All of the potential energy got converted to kinetic energy. All of the work done is equal to the change in kinetic energy. The change in kinetic energy, final minus initial, is 1/2 mv squared. The initial kinetic energy, as we previously established, is 0. So the net work is the result of the force due to gravity times the height, mgh. And as we previously established, all of the potential energy got converted to kinetic energy, meaning the new kinetic energy is equal to the mgh, the energy from gravity. Okay, so that allows us to set up this equation. From there, we can isolate v, by canceling m on both sides, then taking the square root, and you'd get v is equal to the square root of 2gh. All we have to do then is plug in our numbers, and we have v is equal to 19.8 meters per second. So our next task is to determine what is the distance, meaning how far away would the block go from the beginning of region B to where it stops due to this friction. Okay, so now we're looking for the change in distance. Alright, our first thing that we realize is that because the block goes to a complete stop, well, that means all of the energy that the block gained from going down the ramp, that is the potential energy, all of that energy was dissipated. All of that energy was, you can say, used up by the frictional force. Alright, so that would mean that the net work done is equal to 0. We can also establish that by realizing that the net work is equal to the change in kinetic energy. The change in kinetic energy is, well, 1/2 mv squared. Our v final in this case is 0. Our v initial in this case is 0. So we have no change in kinetic energy, going straight from the beginning to end. From here to here, we do have a change in kinetic energy. That's what we solved for. Alright, so that allows us to set up this equation, that the net work is equal to the work done by gravity, i.e. mgh, and the work done by kinetic friction, the force due to kinetic friction. So that's F mu k, and we know that the force due to kinetic friction is equal to the coefficient of kinetic friction times the normal force, and the normal force is mg, times the distance over which that force was acting. Alright, so now we have 0 for our net force, and that allows us to set up this equation. All we did was add mu k mg delta d to both sides, and now we have mu k mg delta d is equal to mgh. Alright, so now we solve for delta d. We can cancel out the mg from both sides, and that leaves mu k delta d is equal to h. Solve for delta d, and that gives us h over mu k, and h is 20, mu k is a half, and that gives you 40 meters. Our next task is to establish what is the net work done. Well, in solving for task B, we actually answered this question, because the net work is the change in kinetic energy. That is our work energy theorem. The net work is our change in kinetic energy. That's a very important point. right? You're going to fall back on that in solving other problems. So, net work is equal to the change in kinetic energy is equal to 0. Alright, our next task is to determine the time it took to slow the block down over here. How long did it take to go from 19.8 meters per second to 0 meters per second? Alright, so we know Newton's second law, F is equal to ma. Ma is equal to negative mu k mg. So you might ask yourself, why? Well, the force due to the coefficient of kinetic friction is acting in the opposite direction to the object's motion. That is, the object is moving in this direction, and the force is acting in this direction. The force due to kinetic friction is acting opposite the object's motion. So if that's the case, they are going to be signified as opposite direction. So I'm going to set that going in this direction from left to right is going to be positive. We've actually previously established that by solving the problem the way we did. But let's clarify now that going from left to right is going to be your positive direction. That means the forces acting from right to left is going to be negative to that. So our net force in region B is the force due to kinetic friction. Net force is equal to ma due to Newton's second law. So net force, ma, is equal to the force due to kinetic friction. That is all we're saying. That is all we've established. Alright, so now we can cancel m from both sides, and we know that acceleration is equal to the change in velocity over time. So now that gives us this equation. The change in velocity over time is equal to mu k times g. And now we can cross multiply, bringing the time over here and the mu kg underneath the delta v, and that gives us time is equal to delta v over negative mu kg. And that equals, well, the final velocity is 0, minus the initial velocity of 19.8, what we solved for in part A, divided by the negative mu k, which was 0.5 in region B, times g, 9.8. Negative divided by negative will give you a positive. 19.8 divided by 0.5 times 9.8 will give you 4.04 seconds. Alright, so to clarify at this point a little further, all this is saying is that the net force is equal to, well, the sum of all the forces acting. We're only focusing on the x direction. So that would mean the only force in the x direction is the force due to kinetic friction. The only force in the x direction is the force due to kinetic friction. That's all this is saying. The force due to kinetic friction is going to be in the opposite direction of the net force, opposite direction of the object's motion. So that is why we are going to have a negative force. Alright, and that's it.